What we're going to be talking about today is something called the change of variables for working inside of double and triple integration, or working with functions in multiple variables. Now, you've actually done change of variables quite a lot. We've actually spent a good amount of time inside of this chapter with the change of variables. Specifically, what we've done is we've gone in a double integral case. What we've done is we've moved from working in rectangular to going into working into polar. Okay, and then when we looked at triple integrals, we went from rectangular to cylindrical or rectangular to spherical. Moving to cylindrical, moving to spherical, moving to polar from rectangular, that's all a change of variable. That's called the change of variable because we went from an xy to an r theta. Now what we're going to do is we're going to say, okay, now let's generalize that process to doing a change of variable into any kind of region. Now, if you remember, the reason why we actually changed the variables in that case was because it made our integration easier. Triple integration and double integration takes an incredible amount of time. It's very hard sometimes to do if we're working with regions that have not been changed into the right kind of variables. And so change of variables, what it allows us to do is it allows us to make the process of doing double and triple integration a lot easier. That's why we want to do it. That's our point of having this happen. So what we're going to do now is we're going to generalize the process. So before, if you remember, we actually had, for example, dA ended up being r dr d theta when we were moving from rectangular into polar. We're going to need to actually be able to figure out how to do that, okay, generally. So not just when we're going to, a cylindrical or a spherical region or to a polar region, but from a planar region to any kind of region, or going from a cylindrical and polar region to any kind of region. How are we going to go about doing that? And that's what we're going to be talking about today, is the process that we use in order to have that happen. In this video, the major piece that we'll use in order to do that process of change of variables is something called the Jacobian. So the Jacobian, it's got a formula. That formula is derived from the determinant. It's a special kind of determinant. And so consequently, kind of look back, think to yourself that determinant, also remember kind of the cross product. And that's going to help us to think about this Jacobian. Okay, so let's get started. So we're going to start out our conversation about change of variables with something called planar transformations. Now, planar transformation, we're only going to be thinking about this in two dimensions. So let's imagine that I've got a plane. We'll have this plane be the xy plane, all right? And inside of the xy plane, I've got a region, okay? And I've got a rectangular region, call it r, all right? And now let's imagine that in that xy plane, or possibly, the r theta plane, what I have now is I have another region, okay? And I'm going to call this region D, okay? And what I want to do is I want to create a transformation. And when we talk about transformation, it's a change. And we're going to list this out as T, okay? T as our transformation. And what T is going to do is T is going to change R into D. That's the idea. T is going to go from R into D, okay? And we're going to have a very special kind of transformation here. We're going to take, in this case, let's imagine that I've got a point UV, and UV in UV in this first plane, the xy plane in R, is going to go over here to xy, okay? So UV will go over to xy along the transformation T. So T, we'll write this. We're going to write that T of UV is equal to xy. All right? That's what it does. That's kind of like, it's like a function, right? It's like a function. Or we also sometimes call it a mapping. It'll also be called a mapping. And so that's what it does in one case. And what we want to think about is that if I picked a different point, let's say I choose another point, call it U2, V2, inside of R, that what I'm going to get is I'm going to get a different point in D, right? Call it X2, Y2, okay? And so then the transformation T of U2, V2 is going to equal X2, Y2, okay? If you want to call these U1, V1, and X1, Y1, you can as well. Doesn't really matter, okay? That's what the transformation does. All right, now I want to imagine that I'm going to take everything that I have in R, all this in R, and I'm going to do that to every single point utilizing D. So what's going to happen is this planar transformation is going to transform T of essentially R will end up equaling D. So T of the region R ends up equaling D. That's what the transformation does, right? So, and like I said before, we could be going from the XY plane into, our theta plane, or we might be looking at it going into some other plane that has a totally different naming and numbering system. That's okay, all right? We just want to imagine that's what's happening with our planar transformation. And that's what we're going to be doing when we actually do our change of variables. We're going to imagine that transformation occurring. So what we've got here is we've got this thing called a one-to-one transformation. And this property here, I've got u2, v2, right, goes to x2, y2, uv goes to xy. And as long as, okay, if t of u1, v1 equals t of u2, v2, then u1, v1 actually equals u2, v2. Now what that means is that, right, no 2 points in R map to the same point in D, right? So essentially that's our idea of a one-to-one transformation, right? If we can take two transformations, we transform 2 points, right, and they end up equaling each other, that means that they actually are the same point, all right? Logically speaking, it makes sense. It's like the only thing that maps to T of u1, v1 is u1, v1, okay? Right? And that's kind of the idea that we're going to work with. And we need for the transformation, for our transformation in this planar transformation to be one-to-one. So planar transformations must be one-to-one. So that's the first thing. And the second thing is that they must have continuous first order partials. Meaning that if we take the first order partial derivative on whatever region that we're looking for, okay, so that basically in this case, for example, we'll look at an example here. To have continuous first order partials, that means that if I take the partial derivative of these functions here, right, of t of u1, v1, right, with respect to u, t of u1, v1 with respect to v, that what I'm going to get is I'm going to get continuous functions. So if we have a transformation t, okay, so we've got a transformation t, and we'll say that t of uv, okay, is going to equal xy, all right? Then sometimes what we're going to need is we're going to need a t inverse of xy, and that'll end up giving me uv, okay? Basically, what we want to imagine is that if we have, say for example, a transformation that goes from the uv plane into the xy plane, and it goes from like a region in the UV plane to, let's say, a rectangle in the XY plane. We've got this transformation T. We want to find another transformation T inverse that will take us backwards. Okay? And the process for doing this is actually not all that terrible. It's actually a pretty easy process. What we're essentially going to do is we're going to be solving a system of equations in order to construct T inverse. Okay? And what T inverse will end up being used for is it'll end up being used for helping us find bounds of integration. It'll end up becoming valuable for us to find something called the Jacobian, which we'll utilize a little bit later on in order to find integrals. So let's say, for example, I take T, and I've got T is going to be the transformation x equals u plus 2v, and y equals negative u plus v, okay? And we're going to have s is going to equal r, which is going to be equal to what we call r squared, or r2, okay? So it's two-dimensional space. So our transformation t, we write it as, here's our domain, r squared. It's going to go to r squared, okay? And essentially, we're going to get that t of uv equals xy. Okay, t of uv is going to end up equaling xy. So what we want to do is we want to find a t inverse that's going to take us from values of x and y to values for u and v. Okay, and that's going to end up becoming really very valuable for us in different, depending upon what we're doing. We're actually going to kind of do this the opposite way around frequently. So what I'm going to do is I'm going to have x equals u plus 2v, okay? And y equals negative u plus v, okay? And I'm going to treat these as a system of equations. And what I want to do is, I need to eliminate, I'm going to try out eliminating u because that's really simple. I'll just add the two equations together. So I get, on one side, I'll get x plus y, and on the other side, I'm just going to get 3v, right? Because 2v plus 1v is 3v. And so then I can just divide by 3, and I get v equals x plus y over 3. So that gives me my v in terms of my x and my y. Now, I'll go over and I'll say, okay, well now I've got x and y. X equals u plus 2v, and y equals negative u plus v. And so if I multiply the bottom by now negative 2, then I can add the two equations together. I'll get x minus 2y, because I'm multiplying y by negative 2, is going to equal, this will be u, negative u times negative 2 is 2, so this is going to be 3u, and then 2v and negative v are going to cancel out, so there it is. There, we're done. Divide by 3, and we get x minus 2y over 3 equals u. So my inverse transformation, T inverse of xy, is going to equal x minus 2y over 3, comma x plus y over 3. And that is our transformation. Or our inverse transformation, should we say. So what we're going to do now is we're going to find the image of a region under a transformation T. And so what we'll do is we'll describe this process. We're going to use an example to describe the process. What we're basically going to do is we're going to start out in this case, something called a UV plane. All right, a UV plane is just a parametrization, right? We have seen before like TS, ST, right, as a parametrization. UV is just another way of parametrizing, all right? And it has just a different coordinate system, right? A different way of writing our coordinates. What's going to end up happening is that we're going to end up getting different regions under these transformations. Remember that these transformations, we want them to be one-to-one. We want them to actually have those first-order continuous partials, which this one does. But we also want to focus in on how is it that we visualize what's happening. So let's start out by drawing the region, okay? So let's imagine that we have this transformation, all right? So the first thing we want to do here is draw the region. We're going to let a transformation T be defined as T of uv equals xy, where x equals u squared minus v squared, and y equals uv. We're going to find the image of the triangle in the UV plane with vertices 0, 0, 0, 1, and 1, 1. So I'm actually going to draw out my region, something a little bit larger so that I get more of a full sense of what it looks like. So here's 0, 0. We'll let this be, here's going to be 0, 1. Okay, and here's 1, 1. So, and so our job is going to be to graph the region in the XY plane. So this is the UV plane. It's going to look like this. Okay, so there's your UV plane. Our job is to draw this in the XY plane. All right, and then also kind of imagine what this transformation is going to look like in different regions of this triangle. Okay, so the first thing you want to get here is that if I have a three-sided figure in the UV plane, it's got to be a three-sided figure in the XY plane. And the reason why is because if one of the sides goes to more than one side or goes to no sides, right, we no longer have that one-to-one transformation. And we possibly also do not have the continuous first-order partials, right? Basically what ends up happening is that we either are breaking the thing apart or it's disappearing, right? And that doesn't work, all right? This is a one-to-one transformation, so a line becomes a line, okay? And it's going to have endpoints and the like. And so consequently, we can think of a three-sided figure in the UV, okay, is going to become a three-sided figure in the XY. Why is that so important? Well, that's so important, okay, so we got to imagine our T. That's so important because we are going to determine the sides of the triangle in XY, okay, by using the sides of the triangle. So like, let me explain what that kind of means, all right? What we're going to look at. We're going to start out here. We're going to start out with this side here, and that side, we're going to call that side A, okay? So we're going to consider side A, and side A has got a couple of characteristics, okay? One, side A has, if this is the U component and that's the V component, then side A has that U equals 0, okay? Excuse me, not U equals 0. That, that U equals 0, and V is going to be greater than or equal to 0 and less than or equal to 1. Okay? So that's what that looks like, right? Here's 0, here's 1. Okay? On our V axis, we go from 0 to 1, and U just stays equal to 0 for that line A. Now let's consider our transformation. X equals U squared minus V squared, and Y equals UV. So X equals U squared minus V squared, and Y equals UV. I'm going to plug in 0 in for U. So I'm going to get X equals negative V squared, and Y is just going to equal 0. Okay? So if Y equals 0 and X equals something that doesn't have any Y's in it, then what we know is that we're just going to get a constant function, right, on that x-axis. So we've got something on the x-axis, and then I need to figure out what my bounds are. So notice my V goes from 0 to 1. So I'm going to get that that X of 0, right, equals negative 0 squared, because this is my equation for X, right, and which equals 0. So X of 0 goes to 0, and Y of 0, Y of 0 is just going to equal 0, right? And then we're going to have that X of negative 1, X of 1 equals negative 1 squared, which equals negative 1. And then again, Y of 1 is just going to equal 0 again, because we've got the constant function 0. All right? So essentially what we've got going on here is that our function, or that line, we're going to be on the x-axis, right? Okay, and it's going to go from X is going to be greater than or equal to 0 and less than or equal to, greater than or equal to negative 1 and less than or equal to 0. Now, by the way, it should be stated that if we're going, if I'm moving upward from 0 to 1, that we're actually moving backwards from 0 to negative 1. If we want to kind of like figure out what that direction is, right on the line. But it doesn't really matter for the moment, okay? We're just going to say, okay, here's my x-axis, here's my y-axis. I'm going to go from 0 to 1, and I'm going to have it at y equals 0. Okay, so y equals 0. All right, and x is going to be greater than or equal to negative 1 and less than or equal to 0. So this is, we'll call this A prime. That's my new side. A transforms to A prime. So we say T of A equals A prime. Now let's take our second side. We'll choose our second side. It's going to be this side. We'll call that B. Notice that for B, V equals 1. Okay? And U is going to go from 0 to 1. Right? There's U equals 0. U equals 1. So I'm going to think about B. Okay? That's going to have that V equals 1. And that U is going to be greater than or equal to 0 and less than or equal to 1. Now I'm going to plug that in. X is going to equal U squared minus 1 squared, so minus 1 squared, which equals U squared minus 1. And Y is going to equal U, because it's going to be U times 1, which equals U. So we no longer have a constant function. So we no longer have a constant function in this case, okay? Instead, we've got something else going on here. So we have y equals u, and x equals u squared minus 1. Okay, so x is going to equal, we'll substitute, is going to equal y squared minus 1. All right, and then our bounds, okay, our bounds are going to have, let's see, what should we do? We're going to have x equals y squared minus 1. So we'll take x of 0 is going to equal 1 squared minus 1, which equals 0. Okay. And so that's the top bounds is 0, and then the bottom bounds x of so that's actually x of 1, excuse me, x of 1, and x of 0 then is going to equal 0 squared minus 1, which equals negative 1. So my x values are going to go from 0 to negative 1. All right. So we can figure out what our y's are if we wanted to. Y is going to go from y is going to be greater than or equal to 0, less than or equal to 1. Okay. So what we're going to be doing is we're going to be in this region again, okay? Because we've got x is going to go from negative 1 to 0, right? Negative 1 to 0, and our y's are going to go from 0 to 1. That's just from plugging the value of u into our equations. And we're going to be, here's going to be our equation, y squared minus 1. Well, what is that, right? That's a sideways parabola, okay? It's a sideways parabola, right, that starts out at negative 1 here. So this ends up becoming b prime. There's b prime right there, and there's the sideways parabola. Okay, y squared minus 1, right, there's the negative 1, there's the y squared part, okay, facing to the right, and then we're going to go from, our x values are going to go from 0 to negative 1, and our y values are going to go from 0 to 1. Finally, let's choose c. We've got c right here. There's that equation. And so if I look at c now, I know that this is y equals x. So the equation there for c, or actually it's just going to be u equals v, or v equals u. Notice that we're in the uv plane, so this line is going to be v equals u. If it was in the xy plane, it'd be y equals x. That's why it's v equals u. Okay? So for c, we've got v equals u. Okay? And in addition to that, my u values are going to go from 0 to 1. So there's u equals 0 to u equals 1. Plug that in now. Okay, we get that x is going to equal u squared minus u squared, right? Because u equals v. We had u squared minus v squared, so it's going to be u squared minus u squared. And y is going to equal then u times u, which equals u squared, right? And just all I did was I plugged it back into my transformation equations. Okay, just plugged it back into my transformation equations. So x is now going to equal 0, y is going to equal u squared, okay? And then if I plug in my values, I'm going to go from 0, and then this is u of 0, which equals 0. So I'm going to go from 0, 0 to 0, and then u of 1 is just going to equal 1 squared, which equals 1 to 1, 0, 1. So I'm going to get the y-axis, x equals 0, from 0 to 1. So this line right here, that's C prime. Okay? And then everything in between, right? That's going to be all the stuff that's in between this region. It's going to be mapped into that region right there. Okay? So what did I do? I took the three sides of my triangle, okay? And I mapped them using the transformation onto the three sides of this new kind of quasi-circular region. It's actually a parabolic region in the xy plane. Okay, a couple things to just notice here. Note that I had to understand how to in fact parametrize these lines. So that's actually an important point. You want to make sure that you can be able to do that, parametrize the points or parametrize the lines. Okay, and then it was just simply a matter of plugging those parametrizations into the equations for x and y. Okay. And once we've done that, that actually gives me my transformation. All right, I'm going to do another example right now. All right, so let's suppose that we have a transformation t, and it's defined as t of uv equals xy, where x equals u plus v, y equals 3v. We're going to find the image of the rectangle, g equals uv, 0 less than or equal to u, less than or equal to 1, v less than, greater than or equal to 0, less than or equal to 2, from the uv plane after the transformation into our region in the xy plane. So we're just going to do that. We're not going to worry about this, show that t is 1 to 1, and then find our inverse function. I'm not going to worry about that at the moment right now. Instead, what I'm just going to do is I'm just going to imagine, how do I find this transformation? So the first thing I'm going to do is I'm going to draw my region. Okay, I'll draw my region first. Okay, so I'm going to go from U. So here's my U, here's my V. U is going to go from 0 to 1. Okay, so there's 0, and then we'll make that 1. Okay, and V is going to go 0 to 2. So that's going to go up here to, there's 2. Okay, and so on the V, that's 0 to 2. So this is my rectangular region right in here. That's what we're going to be looking to transform. So there's my rectangular region. I'm looking to transform that region. Now what I'm going to do is I'm kind of going to think about this in terms of A, B, C, and D. Okay? My A region down here. Okay? I'm going to think about A region right down here. A is going to have that V equals 0. Okay? And that U is going to be greater than or equal to 0 and less than or equal to 1. I'll go down to B now. Consider B. B is going to have that U equals 0. And V is going to be greater than or equal to 0 and less than or equal to 2. Right? Because there's the V. V is going to go from 0 to 2. C region is going to have that V equals 2. And then U is going to be greater than or equal to 0, less than or equal to 1. Right? Because it's going to be horizontal. It's a horizontal line. And then D is going to have that U equals 1, and then V is going to be greater than or equal to 0, less than or equal to 2. So what we're going to do is we're going to transform A, B, C, and D. Okay, I'm going to do this kind of vertically. So we'll start out with A. So, and then let me translate my equations. I've got X equals U plus V, and Y equals 3V. So there's my transformations, okay? So A, right, where A is V equals 0, is going to have that X equals U, right, U plus 0, and Y equals 0. So Y equals 0, meaning that it's on the x-axis, okay? We're going to go U is 0 to 1. So that means that X is going to be greater than or equal to 0 and less than or equal to 1. So I'll draw that in. So I'm going to be on Y equals 0, so I'm going to be on the x-axis, and I'm going to go from 0 to 1. So we're going to have, that means that we're going to go from 0 to 1 in A. Okay, 0 to 1 for A, this is going to be our A prime. Okay, because we get Y equals 0, X equals some U, and X is going to go from 0 to 1. Now let's take a look at B. B is going to go from U equals 0, is going to have that U equals 0. So B, right, has U equals 0, so that means X equals V. And then Y equals 3V. V is going to go from 0 to 2, so that means that X is going to be greater than or equal to 0 and less than or equal to 2. Okay, so we're going to draw the line Y equals 3V, or excuse me, so what we're going to do is we're going to replace X in with V, so we're going to get Y equals 3X. And now I have the equation in my xy plane. So I got Y equals 3x, okay? And I'm going to go from 0 to 2. So there's Y equals 3x. I'm going to draw the line Y equals 3x. So there's that. And notice I went from x goes from 0 to 2, okay? So it's going to go out to that 0 to 2 spot. Okay, and there's B, and this is now B prime. Now we need to figure out C, or C prime. So we're going to take C, and we've got that, so with C, right, we've got V equals 2. So that means that X is going to equal U plus 2, and Y is going to equal 6. So here's the deal, right? If Y equals 6, we got a constant function again. We, in fact, are going to have this line right here, Y equals 6, okay? And then we just need to figure out where we're going from. So we've got U is greater than or equal to 0, less than or equal to 1. So U is going to be, U of 0 is equal to 0 plus 2, so that equals 2. And U of 1 is going to equal 1 plus 2, and that equals 3. Which kind of makes a lot of sense. I mean, basically what you're going to imagine is you're like, well, if it was connected in the UV plane, it should be connected in the XY plane, which it is. Okay? So what we get here is we got that X, excuse me, this is X. We got X is going to go from 2 to 3. along the lines y equals 6. Okay? Finally, we need to find d. We're going to go find d. So we go up here, d, u equals 1, and v is going to be greater than or equal to 0, less than or equal to 2. So that means that x, right, is going to equal v plus 1, right? Because remember, x equals u plus v. And y is going to equal 3v. So v will equal x minus 1. We're going to plug in v into y. So we get y equals 3 times x minus 1, which equals 3x minus 3. Okay? And then what we need to do is we need to figure out what x values we're going to be looking for. So v is going to be greater than or equal to 0, less than or equal to 2. So v goes from 0 to 2. So x of 0 equals 0 plus 1, which equals 1. And x of 2 is going to equal 2 plus 1, which equals 3. So x is going to be greater than or equal to 1 and less than or equal to 3. Okay? So what we'll do then is that we're going to go from 1 to 3. Okay? Yeah, it's that line right there. 3x minus 3, right? If you actually kind of extend this out, you're going to end up right here. Your y-intercept is going to end up being at negative 3, and you're going to have a slope of 3. So this is your new region. It's going to be that parallelogram. Okay? So constructing those transformations, right, it basically means, right, figuring out what the parametrization of each one of those lines are, okay, transforming them into x and y, all right, and then mapping them onto the new plane. Okay? And big thing to remember, if it's four-sided in the UV plane, it's got to be four-sided in the XY plane as well. Right? Because you go side to side. Okay, so now we're going to talk about something called the Jacobian. And we're going to start out with this idea that we have what's called a C1 transformation. A transformation that has continuous first-order partial derivatives is called a C1. So all the stuff that we've been using is these things called the C1. And so for us to have a planar transformation, we're going to have, the transformation has to be, it must be C1, a C1 transformation. Now, what I'm going to imagine is I'm going to imagine that I've got something in the XY plane, right? I've got a rectangle in the XY plane. Let's say, for example, I have a rectangle in the XY plane, call it region R. And I'm going to go into, and something like some other region in, let's call this the UV plane. All right, so now we have the UV plane. And it looks like, I don't know, we'll make it look like this, okay? All right? And so what we know is that essentially, right, that we're going to go line to line. And we don't know which line is going to map to what, but like let's imagine that like we have A maps to A prime, B maps to B prime, C maps to C prime, D maps to D prime. Okay, kind of imagining that's the case. Now, everything in this, in R, we can actually break it up into rectangles, right? Okay, we can break it up into little rectangles, right? And that's how we take an integral. That's how we're going to end up finding our areas. Okay, our little, we call this, that's going to be a delta A, right? And that delta A ends up being delta U times delta V, right? If this whole length, right, is a delta U, and this is a delta V, okay? Now, without getting too much into the weeds of this, what we're going to do is we're going to imagine that over here, we're going to get some parallelograms. Okay, so just like we did in the last one, we kind of generated some parallelograms. So inside of here, we've got some sets of parallelograms, like little parallelograms. And these parallelograms, they map rectangle to parallelogram, right? Rectangle to parallelogram, or not the same rectangle, let's say a different rectangle. Okay, different rectangle to parallelogram. And that's kind of like how they're going to work, okay? So what we're going to need to do is we're going to need to find the area of those parallelograms. We're going to go out, we're going to find the area of those parallelograms. And if you remember from our earlier conversations, right, areas of parallelograms in 2D, right, are cross products. Okay? They're basically, well, they're more than, they are, right? They're cross products, so we're imagining that what we're going to do is we've got the area of one region, which is just simply delta U times delta V, and we're going to actually map it over utilizing some parallelograms. And so this is just kind of like a sketch. It's very hand wavy. I didn't want to get into like the whole partials and then taking the cross product because it's kind of a bear, okay? But what we're going to do is we're going to imagine now that we've got a dA, okay? So we need to find dA. Remember, like if we have a double integral, right? We've got some double integral over a region R. We're going to have our function f of xy times dA, okay? And when, like say for example in polar, dA was equal to r dr d theta. Rectangular, dA was going to equal dx dy, or dy dx, depending upon which order you did it in, doesn't really matter. Okay, so it's dy dx or dx dy. Okay, the Jacobian, it tells us what the function how, let's say, tells us how we will find the area, find the dA. Okay, how are we going to find that change in area? Basically, it's going to tell us, should I use dx dy? Should I use r dr d theta? Should I use something else? Okay, so I'm going to have my function written inside of my variables times the Jacobian, okay, times, you know, whatever else that I might be looking at. Okay, so we're going to define that Jacobian. We're going to take a look at some examples, and hopefully that'll illustrate a little bit about what that Jacobian is. It's basically going to give us that dA, and it gets derived. It's going to be a cross product, and the reason why it's a cross product is essentially that we're going to be transforming into parallelograms. That's essentially what's going on here. And so when you find the areas of parallelograms, what do? You take cross products. Okay, so let's take a look at it. Let's define the Jacobian. Okay, so our definition, the Jacobian of a C1 transformation, T of uv equals G of uv, H of uv, is denoted by J of uv, and is defined by the 2x2 determinant, okay? J of uv equals, and this is the partial of xy over the partial of uv, okay? So, or the magnitude of it, which is going to be this determinant. It's going to be the determinant, the partial of x over du, dy, dv, minus the partial of x over dv over the partial of y with respect to u. Okay, so what we're going to have to do is we're going to have to find some partials. All right, go out and find some partials. And just to make this really clear, that's a v right there, and then this is also a v. So we're going to have to find some partials, then we're going to have to take a determinant, and then that's actually going to end up giving us our Jacobian. Okay, so let's take a look at one that we already know the answer to. So let's say, for example, right, so we've got our example, and we've got a change of variable. We're going to let x equal r cosine theta, and we're going to have that y equals r sine theta. And so we'll utilize this in our first example. We already know that we're going to end up with r dr d theta. Okay, we already know that that's going to be the case, so we know this should end up equaling r. So if I go in here, I'm going to first find the partial of x with respect to r. So xr is going to equal cosine theta, and then x theta is going to equal negative r sine theta. And then yr, okay, is going to equal sine theta, and y theta is going to equal r cosine theta. So essentially we've got, we're going to now take dx du, okay, so we'll take, that's going to be our xr, so we'll have dx dr, okay, we'll have dy dr, dx d theta, and dy d theta. Okay, just keeping, okay, just noticing that like variables, you know, you kind of choose how you want to go. All right, and notice that in this case, we've got our function is r theta, so that's kind of the order that we're going to go in. So this is going to then equal xr, so that's cosine theta, yr sine theta, negative r sine theta, r cosine theta. So now we'll take the cross product, or actually we'll take the determinant. So this is going to give me r cosine squared theta plus, okay, because it's minus, so that minus minus, so it's plus r sine squared theta, which equals r cosine squared theta plus sine squared theta, which just equals r. And we already know that that's going to be the case because remember, right, when we're working in polar, which is what this is, remember that dA equals r dr d theta. Okay, so this thing right there corresponds to that r right there. Okay, and that's our Jacobian. Let's take a look at another example. Okay, so let's say we want to find the Jacobian for t of uv equals xy, and we have this u squared minus v squared and y equals uv. Okay, so first we're going to have to find x, or del x del u, okay, which is just going to equal 2u. And then we'll find del x del v, which equals negative 2v. We'll have del y del u, which equals just, which ends up equaling v. And we'll have del y del v, which equals u. Okay, just by taking the first partial. All right, and there we go. So now I'm going to find that my Jacobian, j of, call this j of uv, is going to equal, it'll be 2u, negative 2v, and then, 2u, negative 2v, and then v, and u. And so that'll be 2u squared plus 2v squared, and that will end up being my Jacobian. All right, now let's get into integration. Okay, so what we've done is we said, okay, all of this is meant to simplify integration. It in fact certainly does. All right, but what we need to do now is we need to like kind of throw that into our integration. So what we're going to say is we're going to let t of uv equals xy, where x equals g of u of v and y equals h of u of v. So basically that's our parametrization of x and y. And it's a 1-to-1 C1 transformation with a non-zero Jacobian. So that's actually very important. On the interior of the region S in the UV plane, it maps S into a region R in the XY plane. If f is continuous on R, then the double integral over the region R of f of xy dA is going to equal the double integral over S. So S is our new region. We had been calling it D, but that's our new region. Okay. We have our new variables du dv, and this whole thing, that's our new dA, right? That's dA under du dv, under u and v, okay? And that is the double integral over S of f of g of uv, h of uv, times the Jacobian times du dv, okay? And that's actually how we find the double integral. So what we're going to do now is we're going to take a look, we're going to do some setups for some double integrals utilizing the change of variables in order to illustrate this point. So let's take a look. We've got, we're going to change our variables from rectangular to polar. We're going to actually go in, we're going to calculate our Jacobian. We actually already know what it is. We know that del f over del g ends up equaling r in this case. So we consider the integral from 0 to 2, 0 to the square root of 2x minus x squared of the square root of x squared plus y squared, dy dx. We'll use the change of variables, x equals r cosine theta and y equals r sine theta. So we know we need to find the double integral over the region S, okay, of, we'll call it, it's going to be f of u of g of uv, comma, h of uv, and then the Jacobian del u, or del xy over del uv du dv, okay? U in this case is r, we'll let v equal theta. Okay, we know that this thing here, we already know that's going to be r, so we're going to have r, so our dA is going to equal r dr d theta. So now all I've got to do is I've got to figure out this, and I've got to figure out the bounds of my integral. okay, which we've done quite a lot of, but we're going to do it again. Okay, so we know x equals r cosine theta, y equals r sine theta. Okay, and so what we have is this is in terms of x and y. So what we'll do is we're going to evaluate, we're going to consider this region. So let's look at the region. Our y value, y is going to be greater than or equal to 0, less than or equal to the square root of 2x minus x squared. And x is going to be greater than or equal to 0, less than or equal to 2. Okay, so we get, let's set y equal to the square root of 2x minus x squared. Okay, so y squared is going to equal 2x minus x squared. And so consequently, if I plug in my y is r sine theta, I'm going to get r sine theta squared is going to equal 2r cosine theta minus r cosine theta squared. Add over, we're going to get r sine squared theta plus, or excuse me, r squared sine squared theta plus r squared cosine squared theta equals 2r cosine theta. So this is then going to be r squared equals 2r cosine theta divided by r. We end up with r, well, actually what we're going to do is we're going to first that r could equal 0, okay, and then or we'll divide through by r, and we get r equals 2 cosine theta. Okay, so our r's are going to be bounded. R is going to be greater than or equal to 0, less than or equal to 2 cosine theta. Okay. So now I'm going to kind of envision what this region actually looks like. Okay, and so the region, the square root of 2x minus x squared is in fact going to be, it's a half circle. Okay, 1, 2, 3, 4. Okay, let's imagine that's 1, that's 2, and we're going to get this half circle here, right? Not centered at the origin, but it's got a radius of 1 there. All right, and so consequently, what we're looking for is we're actually going to be going from theta equals 0. Okay, so if I look here, that r equals 2 cosine theta, right? It's going to go from r equals 2 to r equals 0, right? So here's r equals 0, here's r equals 2. So if I write that out, I've got 2 equals 2 cosine theta, okay? So that equals, cosine theta equals 1. That ends up giving me that theta equals 0. And then I have 0 equals 2 cosine theta again. So cosine theta equals 0. So we end up with that theta is going to equal pi over 2. So that gives me my other set of bounds. So my first set of bounds, okay, is going to go r greater than or equal to 0, less than or equal to 2 cosine theta. And my second set of bounds for theta is going to go from 0 to pi over 2. So that's great, because that means that now I have the integral from 0 to pi over 2, comma 0 to 2 cosine theta, and then I've got f of g of uv, or g of, in this case, r theta, and h of r theta. Okay, and then I'm going to have r dr d theta. I've already got those things already set up. I'm pretty good thus far. So now I'm going to say, okay, well, if I take x equals r cosine theta, y equals r sine theta, well, actually I already know. This is the square root of x squared plus y squared, so that's r, right? Square root of x squared plus y squared is r. So this is going to then be just the integral from 0 to pi over 2, 0 to 2 cosine theta, and this is going to be r times r dr d theta. So this is end up being the integral from 0 to pi over 2, the integral from 0 to 2 cosine theta, r squared dr d theta. And we are done. That is our setup. Okay? Let's take a look at one which, in which we're actually just going to go from the very beginning. We're going to do this from the very beginning. It's going to take us a minute or two in order to do it, but I think it would be good just to, so you can see constructing the Jacobian, changing over our bounds, changing over our function, putting it all together so that we have a true change of variables. All right, so let's consider this integral. We want to find the region over a rectangle R of x minus y dy dx, where R is a parallelogram that joins these points 1, 2, 3, 4, 4, 3, and 6, 5. We're going to make an appropriate change of variable, and then we're going to write the resulting integral. So what we want to do is we want to make this as simple as possible for ourselves. So what I'm going to do is I'm actually going to consider the sides of this rectangle, okay, in terms of my xy. And so I'm going to look at, I've got this first line right here, okay, and that first line, if we think about it, it's going to have, we'll call that line L1. So L1, or that first side, is going to equal, it's going to be, let's see, 4 minus 2 over 3 minus 1, which equals just 1, or 2 over 2, which equals 1. So that's its slope. So it's going to have a slope of x. We'll plug it in. We're going to get y. Let's say y minus 2 equals 1 times x minus 1. So that means y minus 2 equals x minus 1. So y equals x plus 1. So that's line 1. And if you notice the parallelogram, so the slope of this side is also going to be exactly the same. It's going to equal to 1. So we'll just take, call this line 2. Line 2 is going to equal then, or is going to give us y minus 3 equals x times, or excuse me, 1 times x minus 4. And so that's going to end up being y minus 3 equals x minus 4. So that y equals x minus 1. So that's my second line. We'll now take a look. Let's do the bottom line here because, again, like I said, it's a parallelogram. So we just need to figure out what the slope is for that value. So we'll call this line 3. So line 3 is going to be have a slope m equal to 3 minus 2 over 4 minus 1. So that ends up equaling 1 over 3. So it's 1/3. So the line is now going to be, we'll use the slope-intercept form. We're going to get y minus 2 equals 1/3 x minus 1. So that's y minus 2 equals 1/3 x minus 1/3. So y is going to equal 1/3 x plus, and that'll give me then 5 over 3. And for line 4, that line right there, line 4, slope is still 1/3, so we're going to get y minus 3, or excuse me, y minus 4. We'll take this point, 3, 4. Y minus 4 equals 1/3 times x minus 3. And so that means that y minus 4 equals 1/3 x minus 1. So y equals 1/3 x plus 3. Now what we need to do is we now need to figure out what the functions are for u and v, right, that will allow me to, in fact, create, a simple function here for my rectangle R, all right? I mean, and what I really do want is I really do want a rectangle, right? A rectangle is going to be the easiest thing for me to actually integrate over. Think about a double integral over a rectangle. It's just, we end up with constants at each stage, so we're not going to, get more and more complex functions. We'd rather have just a rectangle here. So how do I create that rectangle? Like what is it that I'm going to need there to have a rectangle? So what I want, preferably, okay, is I want that u is going to be greater than or equal to some const a and less than or equal to some b. And then I want v is greater than or equal to some c and less than or equal to some d. Okay? And then that would actually end up being just a rectangle, very easy to integrate over because we'd be over some constants. So let's take a look at our functions here, okay? And so if I actually, we'll take a look at these first two lines, right? Y equals x plus 1, y equals x minus 1, all right? So if I start out with those, the far left hand and the far right hand regions, then what I can do is I could say, okay, well, let's take a look. If I let u equal to x minus y, okay, let u equal to x minus y, and when I do that, right, notice that y equals x plus 1. So u is going to equal x minus x plus 1, okay, which just equals negative 1. All right, so for that line, for this line right here, what we're going to get is we're going to get this line, right, starting at u equals negative 1, okay, and then if I take the other line, this line right here, okay, I'm going to get u equals, and this is going to be x minus, and then this is going to be x minus 1, okay, and then that ends up equaling plus 1. So u is going to be bounded by negative 1 to 1. Okay? So, well, I'm going to take a look at that and I'm going to go, that's kind of handy, right? Notice that all I needed was something that basically had the same slope because I wanted to get rid of my x values here. I want to get rid of my x values. And when I plugged in y equals, right, these functions, y equals x plus 1, y equals x minus 1, I ended up with bounds for u of negative 1 and 1. So let's take a look at the other two. I've got y equals 1/3 x plus 5/3, and I've got y equals 1/3 x plus 3. Well, if I let v, okay, equal x minus 3y, right, notice that the 1/3 x is going to cancel out my x's. My x's are going to go away then, okay? If I let x equal x minus 3y, then what I get for the bounds for v now, so I'm going to get v equals x minus 3 times 1/3 x plus 5/3. Okay, and so that's going to end up equaling x minus 5, which equals negative 5. So that's going to be one bound for v, and then I'm going to have v equals now x minus 3 times, and we'll use the other one, that's going to be 1/3 x plus 3, and so that equals x minus 9, which equals negative 9. So that gives me my bounds of v greater than or equal to negative 9 and less than or equal to negative 5. So these actually turn out to be really tidy, very, very handy equations for us to use as a change of variable. All right. Now here's the thing. Is there only one right change of variable? The answer is no. Okay. There's just ones that make things simpler, and there are ones that make things harder. Okay. So this one actually just makes things simpler. Notice also that if I look at my integral, x minus y dy dx, oh my goodness, that means that I'm just going to be plugging in u into here for x minus y. All right. That makes things so much easier there too. So this kind of like this way of writing u and v gives me a rectangular region, right? U between negative 1 and 1, v between negative 9 and negative 5, and it also makes my integral simpler. Okay, so these are all considerations that we can actually kind of make here. So now that we have this, right? So we're going to have an integral, and let's have the integral go from 0, or not 0, but negative 1 to 1. Okay, and then integral from negative 5 to negative 9, right? Then we're going to notice that u equals x minus y, so this is going to be u, and then it'll be dA. So we're going to need to figure out what that dA is. So now recall that dA is going to equal our Jacobian, j of uv, that Jacobian, and this in our case is going to end up being dv du. So the Jacobian, right, j of uv is going to equal del x, del u, del x, del v, and then del x, del y, del u. So the Jacobian, j of uv, is going to equal del x, del u, del x, del v, del y, del u, del y, del v. So what that means for us is that we're actually going to have to rewrite x and v, or u and v into x and y's. Because we're going to have to take the partials with respect to u, partials with respect to v. So right now we have u equals x minus y, and we have v equals x minus 3y. So what we're going to need to do is we're going to need to transform those into functions of x and y. So what we're going to get here is that u is going to equal, u plus y is equal to x. Then we're going to plug that in. We're going to get v equals. So what we'll need to do, we'll need to remember, okay, that u is going to equal x minus y, and v equals x minus 3y. Okay, so we'll start out, we'll multiply times 3. Okay, so that gives me then that u equals 3x minus 3y, and v will then equal, 3u equals 3x minus 3y, and then v will equal x minus 3y. And it's a system, so we're just going to subtract the two. So we're going to get 3u minus v is going to equal 2x, right? Because those two are going to cancel. So x is going to equal 3u minus v over 2. Okay? Now we'll go in, we'll do the same thing with respect to for x. So we're going to have u equal to x minus y again, v equal to x minus 3y. And so we'll subtract the two of those together. We're going to get u minus v is going to equal, these two are going to cancel, and then we're going to get negative y plus 2y, so this plus 3y is going to be 2y. So then that means that y equals u minus v over 2. Okay, so basically we're going to solve a system of equations for each one of the variables. So now what I have is that 3u minus v over 2 equals x, and I have y equals u minus v over 2. So del x del u now is going to equal 3 halves, right? Because it's just going to be these two, right? Because v is treated as a constant. Del x del v is going to equal negative 1/2. Del y del u is going to equal 1/2. And del y del v is going to end up equaling negative 1/2. So we take our partials, and now we can go and find our Jacobian. Right? So there's our partials. And now our Jacobian, j of uv, is going to equal del x del u, that's 3 halves. Then del x del v, that's negative 1/2. Del y del u, 1/2. Del y del v, negative 1/2. So this ends up giving me negative 3 over 4 plus 1 over 4, which equals negative 1/2. And that's my Jacobian. Now remember, we want the absolute value, so because it's an area, so our Jacobian is actually going to be the absolute value of negative 1/2, which equals just 1/2. So my integral, I'm going to integrate, and I'm going to go from negative 5 to negative 9, and I've got negative 1 to 1. Those are my bounds. And then we notice that, remember, u equals x minus y, that was our integrand. So that's u times 1/2, my Jacobian, and then dv du. So it's going to end up being the integral negative 1 to 1, negative 5 to negative 9, 1/2 u dv du. And that ends up being our integral, or our double integral. So much simpler to compute, right? I know it took a lot to kind of like think through the whole process. Once you get better at thinking through the process, it takes less time than it actually takes to calculate the entire integral. Okay? So we went in, we drew out our region, okay? And then from the drawing out of our region, we considered values for u and v that would actually give us, a pretty simple set of bounds and would also simplify our integrand, right? That's why we chose x minus y. That's why we chose x minus 3y, okay? Then we said, okay, now we've got that. Now we just got to go take those, rewrite u and v in terms of x and y, okay? So we can find our Jacobian. Once we found our Jacobian, we plug that into our integral, okay? And now we can go through and actually calculate our integral. All right, so now let's take a look at another example. Let's suppose we want to find the region R of 4x minus 2y over negative 4x minus 6y dA, where R is the parallelogram enclosed by, and we basically, here are the sides. 4x minus 2y equals 0, 4x minus 2y equals 5, negative 4x minus 6y equals 1, and negative 4x minus 6y equals 3. Okay, so what we're going to need to do here is we're going to notice, okay, look, it's 4x minus 2y, and we've got the two sides of our parallelogram are 4x minus 2y, so it makes sense to say, okay, let's let u equal 4x minus 2y. Okay, and then we see our bottom is negative 4x minus 6y, and we notice that we also have negative 4x minus 6y here for v, and negative 4x minus 6y down here, and so let's let v equal that. So v is going to be negative 4x minus 6y, and that ends up being our v. So that actually makes a lot of sense just in terms of this will then be just u over v. Straight up, very simple. Now what we're going to need to do, we've got 4x, what we notice is we're going to notice our bounds. So notice 4x minus 2y is going to go from 0 to 5. Okay, so u, which is 4x minus 2y, is going to be greater than or equal to 0 and less than or equal to 5. Then v, notice that v is negative 4x minus 6y, so v is going to be greater than or equal to 1 and less than or equal to 3. Okay, so that gives us our u and our v. Now what we need to do is we actually need to find the inverse transformation here. And the reason why we're going to need to find our t inverse of, in this case, xy, t inverse of uv, right, to give us our x and y, because we're going to need that for the Jacobian. So this is needed for the Jacobian. So what we'll do then is we're going to say, okay, let's consider this. I've got 4x minus 2y, and then I've got, and that's u, and then I've got negative 4x minus 6y, and that's v. So if I just look at this, I can just add the two of them together. So u plus v, these two will cancel, and this gives me negative 2y and negative 6y, so this becomes negative 8y. So y equals u plus v divided by negative 8. Take that again, I've got u and v. Next time we want to eliminate our y's. So that equals 4x minus 2y, and this equals negative 4x minus 6y. So we'll multiply the top part by, let's say, negative 3. So what that gives me then is that's negative 3u, so this is going to be negative 3u plus v equals, and then this is going to be negative 12x and negative 4x, so that's going to be negative 16x. And then these two are going to cancel. Just with our system of equations, we can divide through by negative 16. So negative 3u plus v over negative 16 is equal to x. So that gives me my inverse transformation. So basically t inverse of uv, or excuse me, t inverse of xy, sorry, it should be t inverse of xy. That's going to give me uv. And that's going to then be u plus, or excuse me, negative 3u plus v over 16, comma, u plus v over negative 8. Okay? And that's t inverse. So we're going to utilize t inverse in order to find the Jacobian. So j of uv, right, is going to equal del x del u del x del v del y del u del y del v. That ends up equaling then, if we take del x del u, that's going to be negative 3/16. Del x del v is going to end up being 1/16, or that negative is negative, that actually switches signs, right? Sorry about that, that's the signs. So this actually gives me 3/16. I get negative 1/16 for del x del u. Okay, I got negative 1/8 for del y del u, and negative 1/8 del y del v. Now we'll multiply. I got negative 3 over 128. And then this will be minus 1 over 128. So that ends up equaling negative 4 over 128, which equals negative 1 over 26. Excuse me, not 26, 32. Okay, so our Jacobian then, though, is going to be an absolute value. Forgot to put that in there, so it's actually going to end up being 1 over 32. Okay, so there we are. Now, if I go in here, all right, I've got my nice rectangular region, u greater than or equal to 0, less than or equal to 5, v greater than or equal to 1, less than or equal to 3. All right, and notice that 4x minus 2y, that's u, negative 4x minus 6y, that's v. So this is going to end up being u over v. So this is going to be the integral, and this will be u over v times 1/32, and we'll do du dv. So 0 to 5, it's du, and then 1 to 3, that's dv. And that's our integral. Okay? In this case, we selected the simplest equations. We didn't even have to draw the region because the simplest equations ended up giving us the easiest regions to work with. Okay, so that kind of like demonstrates for us how it is that we can kind of take a general region and pick some things that will make our process a lot easier to work with, or that'll make our process a lot easier to do. All right, so now let's evaluate this. We got a change of variables now. We're going to do this for triple integrals, and you know, essentially it's going to be the same process. It's a little bit more involved, but conceptually it's the exact same process. We're going to construct a set of equations that will represent our change of variable. And then what we'll do is then we'll calculate our Jacobian, okay? And then that'll actually constitute the setup for our function, or excuse me, our integral, our triple integral. So basically, if we let t of u v w equal xyz, where x is equal to g of u v w, y equals h of u v w, and z equals k of u v w, and it's a 1-to-1 C1 transformation with a non-zero Jacobian that maps the region G in the u v w plane into the region D in the xyz plane. If f is continuous on D, so big F being the function, then the triple integral over the region R of f of xyz dv is equal to the triple integral over g of f of g of u v w, h of u v w, k of u v w, times the Jacobian with respect to xyz with respect to u v w, du, dv, dw. Okay? And that's it. So let's actually take a look at an example, and I think that actually will be better for us in terms of seeing how this actually works. All right, now let's evaluate this triple integral using some change of variables. So we've got the integral from 0 to 3, 0 to 4, integral y over 2 to y over 2 plus 1, x plus z over 3 dx dy dz. And we're going to do that in the xyz space by using the transformation u equals 2x minus y over 2, v equals y over 2, and w equals z over 3. Okay? So what we're going to start out with is we're going to start out by finding our bounds. So we're going to note that x is going to be greater than or equal to y over 2 and less than or equal to y over 2 plus 1. That y is going to be greater than or equal to 0, less than or equal to 4. And that z is going to be greater than or equal to 0 and less than or equal to 3. So we're first going to find the bounds for u. Now notice that u is equal to 2x minus y. So what I'm going to do is I'm going to substitute in these bounds for y. So the bottom end of u, well, we'll imagine that u is going to be greater than or equal to, and this is going to be 2 times y over 2 minus y divided by 2. Okay, notice all I did was I just plugged in the value for x. Then that's going to be less than or equal to, and this will be then 2, and then our other value, y over 2 plus 1 minus y over 2. And so that then gives me, when I actually throw that in, that's going to be y minus y over 2, so that's going to be 0, less than or equal to u, less than or equal to, and then this is going to be 2, it's going to be y plus 2 minus y, so that's 2 over 2, so that's going to be 1. Now v notice is y over 2, so that's going to be, v is going to be greater than or equal to 4 over 2, and less than or equal to, greater than or equal to 0 over 2, and less than or equal to 4 over 2. So that means that we're going to get v is greater than or equal to 0 and less than or equal to 2. And then we're going to have that z is greater than or equal to, not z, but w is going to be z over 3, so it's going to be 3 over 3, greater than or equal to 0 over 3 and less than or equal to 3 over 3. So we're going to get that w is going to be greater than or equal to 0 and less than or equal to 1. And so those are going to be the bounds for our integral. Now we need to figure out what our function is going to be. Okay, so I've got, notice that u is equal to 2x minus y over 2. All right, and then I have w equals z over 3. And then I have that v equals y over 2. Okay, so if I rewrite this x plus z over 3, right, that's my f of x, y, z equals x plus z over 3. I'm just going to look at this. I'm going to get kind of clever about the whole thing. I'm going to notice that u equals 2x over 2 minus y over 2. And so that then is going to be x minus y over 2, which is just equal to x minus v. So that means, right, that u equals x minus v. So that means that x equals u plus v. Then w equals z over 3. So f of x, y, z that we have over here is going to equal, okay, u plus v plus w. So that's our function. So now I found my function, right? I found my bounds. That was my first thing to do. My function, f of g of u vw, g of u vw, okay, right? Changing f of x, y, z from x plus z over 3 to g of u vw. It's the inverse transformation, by the way. And there we go. Now, what I need to do is I now need to go in and I need to find that Jacobian. Okay, so I got g of u v w. Well, actually, my functions, right? I have that x equals u plus v. Right? I found that. That was my inverse. I know that w equals z over 3. Okay. And I know that v equals y over 2. So what I'm going to do is I'm going to say, oh, well, I'm going to keep x, right? Because I'm going to need to take the partials with respect to u, v, and w. I'll need to change this to 3w equals z. And I'll need to change this to 2v equals y, right? I'm going to find t inverse. That's my inverse transformation. That's t inverse, not the other one around. So here's t inverse. So now I've got my x's on top, then my y's, then my z's. So del x, del u, del x, del v, del x, del w, del y, del u, del x, del v, del y, del v, del y, del w, and then del z, del u, del z, del v, del z, del W. And then we're going to go find the determinant of that. So we got a little bit of work to do here. We got to find some partials. Del x del u is 1, right? Del x del v is 1. Del x del w, no w's in x, so that's going to be 0. Del y del u, okay, look at y equals 2v, that's got a 0 there. Del y del v, that's going to be 2. Del y del w is going to be 0. Del z del u, okay, del z del u, no u's and z's, so 0. Del z del v, okay, is going to be del z del v, that's also 0. And del z del w is 3. So now our job is just to take the determinant of that. So we're going to get 1 times, and then 2 times 3. So it's 2 times 3 minus 0. Minus, and this will be 1 times 0 times 3, 0 times 0, so it's 1 times 0, plus 0 times, and this is just going to be 0 minus 2 times 0. So this ends up being equal to 6. And our Jacobian is an absolute value. Absolute value about 6 is just 6. So now we've got the three pieces. We've got our Jacobian, we've got our function in terms of u, v, and w, and we've got the bounds of integration. So now I've just got to put that all together in my triple integral. So 1, 2, 3. My Jacobian is 6, and we'll figure out what our bounds are in just a second. We'll start out, we'll do, let's do u first. We'll do u first. So u went from 0 to 1. V went from 0 to 2. And W went from 0 to 1. So this means that's going to go du, dv, dw. That's going to be our order of integration. And then we've got our function u plus v plus w. So this is going to be u plus v plus w. And that's the setup for our triple integral. So what did we do? We went in, we figured out our bounds of integration. Okay. Then we figured out what our function was in terms of, in this case, u, v, and w inside of our new grouping. Then we went out and we found the Jacobian. Okay. Notice that in order to find the Jacobian, we had to actually find the inverse transformation. Right? We needed to figure out what x, y, and z were in terms of u, v, and w. We start out with u, v, and w. We need to actually use an inverse transformation in order to get what x, y, and z are. Okay? And that's just basically solving a system of equations. All right? So that actually is a demonstration of how to do a triple integral using a change of variables. All right, so there's a lot going on here. My hope is actually to clean up this video quite a little bit. Now that I've done it once through, I think I have another way of doing it. So as soon as I get a chance to do that, I will. Hopefully this actually kind of helps you to set up and do the Jacobian, at the very least, given u, v, and w. The challenging thing to do is to figure out what u, v, and w are if you're actually just given your normal integral and your region. And so hopefully you can kind of see, there's a little bit of an art to it, right? Figuring out what things might be the simplest things to use, okay, in order to use the change, or to change your variables around, all right? Notice cylindrical, spherical, polar, those are all change of variables. They still work for change of variable. So you can still use those. And also, big idea here is your Jacobian. How does your Jacobian work? And so hopefully this kind of helps to clarify how it is that we're going to do change of variables for double and triple integrals.